All right, so in this video, we'll do a quick overview of the solution method for these perfect substitutes and then a quick numerical example. So in that other video, I kind of showed you how to identify these perfect substitutes. It's when there's a constant constant MRS, right? Marginal rate of substitution. So you can always identify them by just saying that the marginal rate of substitution is constant. And kind of what that means, if we have a constant marginal rate of substitution, let's say I have two goods, let's call them X and Y. So for example, we had some utility function, let's say it's 2x plus y. We could see that the MRS is the negative ratio of marginal utilities, just like usual, and this is going to be negative 2 over 1. So there's a constant marginal rate of substitution, which means these slopes of these indifference curves are like they're a constant slope, right? So we can't use that tangency condition anymore because there's not going to be a tangency condition when we have a budget line that's straight, assuming the budget line's straight, or linear. If we have a linear budget line and a linear MRS, we're not going to be able to use a tangency condition, right? So the key here is to start comparing the slope. So, let's say that this red line is our indifference curve. I'm just going to call it I0. Here it's negative 2. So whether we consume only good Y, only good X, or some combination of the two, which is going to end up with an infinite number of solutions, is going to depend on the slope of the budget constraint compared to the slope of this indifference curve. So as soon as you see these perfect substitutes, we know we have to compare the slope of the budget to the slope of the indifference curve. So there's kind of three possibilities here. When we compare these slopes, right? The budget line is flatter than the IC. I'm going to say IC for indifference curve. So think about what that looks like. Here's Y and X. Let's say, again, this is our indifference curve. And now our budget constraint, I'm going to do it in green, is flatter. The highest indifference curve we're going to be able to reach, the furthest one away from the origin, if they're both goods, we want to get as far the highest indifference curve possible, is only going to be consuming good X here. So X star is going to be spending our whole budget on good X, and Y star is going to be equal to 0. So if the budget line is flatter than the indifference curve, only by, I'm going to call it good 1, but good X here. So X star is going to be M over, P1 or whatever we want to call it, or Px, I guess. And Y star is going to be equal to 0. All right, sorry for that beep. So the next possibility is going to be the budget line is steeper than the indifference curve. And we could draw out that possibility as well over here. Here's X and here's Y. And now what's happening is we have a budget line that's something like this. It's steep. And our indifference curve looks something like that. I0, and this is our budget line. Again, this is the budget line in case that's not clear. That's supposed to say line. My writing's just as bad on this as it is in class. So we see here the highest, if the budget line is steeper than the indifference curve, the highest indifference curve we can get on is if we only spend all of our money on good Y. And we're going to buy no good X. So if this is the case, we're only going to buy good 2. X star is going to be equal to 0, and Y star is going to be equal to M over Py. And the last possibility is kind of, this last case if they have the same slope. And this is kind of a tricky case because really we don't know where they're going to consume because they don't really care where they're going to consume. budget line and IC have same slope, have the same slope. So I mean, we can draw that, but it's going to be like a red and a green line right on top of each other, right? So let's say this is our indifference curve, and here's our budget constraint, like right on top. We really we don't care, where we consume along this line. We could only buy good Y, we can only buy good X, or we can buy any combination as long as we spend all of our budget. So we know that X star is going to be somewhere between 0 and spending our whole money on it. And we know that Y star is going to be somewhere between 0 and spending all of our money on Y. All we have to make sure is that we're spending our whole budget. And I mean, all we can spend is our entire budget. We can't spend more, and we don't want to spend less if we're trying to maximize our utility. So we know it's going to be somewhere between 0 and m over px for each of these for good x, and m over 0 and m over py for good y. And we're spending our whole budget, so we're somewhere along this budget line. So that's the key when we're trying to solve these perfect substitutes, is just kind of comparing the slopes of these, the indifference curve and the budget constraint. So let's go down and look at an example. Again, this example is one of the ones we were trying to get to in the demand chapter. So Tina is responsible for purchasing hand soaps for her household. There are two types that she can choose from, the regular hand soap and the concentrated hand soap. In terms of how much utility Tina's household can get from using hand soaps, 1 unit of concentrated hand soap is equivalent of 3 units of regular hand soap. Let X denote the amount of concentrated hand soap. Let Y denote the amount of regular hand soap. Write down one possible utility function for Tina's household and draw 2 possible indifference curves for this utility function. It's one possible because obviously it's, you could have monotonic transformations. So I'm going to write down what I think is maybe the simplest kind of one, or one of the simplest ones. But you could obviously have a different utility function as long as it is consistent with these preferences. So your diagram should be carefully labeled, including intercepts, slopes, indicating total utility associated with each indifference curve. Okay. So what the question is basically telling us is 2 kinds of soap. X is concentrated, Y is, not concentrated or regular soap. And she gets 3 times the amount of utility from concentrated than regular soap. The one possible utility function would be like 3x plus y here. Obviously, it could be like x plus 1/3 y would be the same thing. It's, there's different ways of expressing the same utility function. And that's not going to change the answer. Okay, so here's her indifference curve, or sorry, her preferences, or her utility function, I should say. And the next part of the question is write down one possible utility function and draw 2 possible indifference curves. Okay. So we want to draw 2 difference curves. Let's pick something that's going to work in terms of round numbers. So let's say what combinations of x and y are going to give us a utility of 3? And we can just rearrange this and we get y equals 3 minus 3x. We could figure out the one that gives her 6 utility. I'm just using these because I know the numbers are going to work out nicely just looking at it. Y equals 6 minus 3x. All right, so we want to draw these. We're just drawing these 2 functions, or these 2 lines, I should say. Here's y and here's x. We can see right away that the slope is -3, which again, this is the marginal rate of substitution is equal to the ratio of marginal utilities. If we took the partial derivative with respect to x, we'd get 3. I'm going to put a negative sign so don't forget it. Partial derivative with respect to y, we get a 1, so that's why it's -3, right, is the slope. So we have 2 lines here. Here are 2 indifference curves. Let's pretend they both have the same slope, -3. This is going to be 3 and 1. and 6 and 2. And here are two indifference curve representing total utility of 6 and total utility of 3. Okay, so hopefully that's not too bad. So now we know if these indifference curves are flat, or they're straight lines. So we can see right away the marginal rate of substitution is constant. So we know we have perfect substitutes. And so the next part, when we're giving prices, we're going to have to use this method we just discussed in order to figure out how much she should buy of each. So question B, or part B, I should say. Suppose the price of concentrated soap is $2.50 and the price of regular soap is $1 and Tina's budget is $10. What is her optimal bundle? Draw a diagram of your solution. Maybe we can just see from the numbers what it's going to be, but should just be a little bit careful about making sure we understand the method, so we can't just like write down a list. So her problem is to maximize 3x plus y, that's her utility function. She gets to pick x and y, and our budget constraint is 2.5x plus y equals 10, right? 10 is her budget, 2.5 is the price of good x, 1 is the price of good y. So now we need to use this solution where we're only going to compare the slopes of the indifference curves to the slope of the budget constraint. So we know right away that the MRS is equal to -3, right? It's a negative ratio of margin utilities. Margin utility of good 1 is 3. Margin utility of good y, of good x is 3. Margin utility of good y is 1. So -3 over 1 is -3. And the slope of the budget constraint, here it's nice and simple because it's nice and linear, is negative px over py, which is negative 2.5 over 1 equals negative 2.5. So we can see, if we compare these slopes, maybe I'll put it down here, equals negative 2.5, slope of the budget. If we compare these two, we can see that the budget constraint is flatter than the indifference curve, right? Hopefully we can see that. I'll write it down, but so if we were going to draw a solution to this, so we're only going to spend our money on good x here. If we wanted to draw what this looks like, here's good y and here's good x. X is the concentrated soap, right? Our budget constraint, I think I've been drawing it in green. We could buy, if we have $10 and the price of good y is $10, is $1, we could buy 10 of them. The price of concentrated soap is $2.50, so with our $10 we could buy 4 of them. So I guess I should be a little bit more careful here. The slope is negative 2.5. And we're going to have some indifference curve that's steeper, right? It has a slope of -3. And so we're only going to buy good x. So x star is going to be equal to m over px, which is 10 over 2.5, which is 4. So x star equals 4, y equals 0. So here's our solution, our algebraic solution. We know that with this utility, with 4 units of x star, it's 3x star plus y. We know that's going to give our total utility of sorry, that's going to give her a total utility of 12. So this is going to be 12 up here. So she only spent her money on, if she had 12 bucks and she only spent her money on good Y, she'd have the same utility of 12. So here's a diagram of our solution. We have the slopes of the two lines, the indifference curve and the budget constraint. And we argued why we're going to only buy good X here because the budget constraint is flatter than the indifference curve, has a slope of negative 2.5, while the slope of the indifference curve is negative 3. And that's how we came up with our solution. So here's a numerical example. I'm going to make another video that goes through the more generic solution if we just had prices of PX and a price of PY and a budget of M, how we think about doing the demand functions for that. So I'll make another video again and make separate videos for these kind of general solutions where we derive the demand functions.